When Alex did a video on linked lists, there was a lot of comments on it, sort of saying, oh, why would you use a linked list? Arrays are faster, what's the point of a linked list? And so I was sort of thinking about this and thought, well, actually, are arrays faster than the linked list? Or isn't the linked list faster than an array? How would we go about finding out which one's faster? So let's have a shootout, arrays versus linked list. The best place to start is actually just remind yourself what the difference is between a linked list and an array. So let's start with the array because they're probably the simplest to understand. So an array is just a way of storing several values in memory. So we start off with the first value, and for the purposes of this demonstration I'm going to use a structure containing multiple values. We did talk about objects a while ago. Structures are what you had before we sort of did objects, so just a collection of values in memory. So I'm going to store two integer values. So this is array element 0, and it's got two numbers. We've then got array element 1, and it's got two numbers. Looks like I'm playing breakout. Got array element 2, and it's got two numbers. And so we can refer to any of these by reference to the index. It starts at 0, 3, 4, 5, 6, 7, 10. So you can have an array of any size, but you have to know how big it is you want it to be when you create it. So you allocate the memory for all the things, and then you can store some values. So we can write 42 in this one, we could put 21 in here, we could put 3 in that one. And we can store them, and we can put different values in here as well as we need them. So that's how an array works. Just one big block of memory, each thing stored one after the other. Linked lists work slightly different. We start off at the beginning of the linked list and it points at nothing. But then as we add things to the list, we allocate the memory for it. We're still going to store two things. So the first thing, we'll label these things inside it P and Q. So we've still got P here and we've got Q. But we also have an extra thing that tells us where the next thing will be, and that's empty to start with. So we'll put 42 and 16. So we just allocate space for that one structure, that one thing that we're going to store. And we connect it up, so we point this at the first thing. So we often call this something like first, and something you can see Alex videos to see how this is done. Then when we want to store the next thing, we allocate space for another one, and we can store the values in. So we've still got 8, we've got 21 in it. Now the difference between this is this could be anywhere else in memory, and we connect up the next pointer to point in to the next thing. So we have some known starting point which points to the first thing, then the first thing points to the second thing, and the second thing would point to the third thing, and so on, and that would point down. And these can be all over anywhere in the computer's memory. And then at the end you normally point it at some known value which is often referred to as null, and is often the number 0. So you can then walk through your list, and when you find that the next point is 0 or null, you know you've come to the end of it. So there are two different ways of storing data. They both store the same amount of data. Now you've got some differences. This one, as Alex says, is fixed in size. When you create it, you can store how many things you know have actually filled in, but as soon as you get more than 11, it's a spinal tap array, you can't go past 11.
If you can see, the numbers all go to 11.
On this, however, if we wanted to put something else thing, we can just get rid of this thing and update this to point to a new thing. So we can make this grow quite easily, and we can also be really clever. We can add things in the middle and the beginning very, very simply. But we're not going to go into that today. So creating them, we're probably only going to do once, but which one is actually faster? Well, let's think about what we actually need to do. Let's define a very, very simple problem. We've created a structure here and it's got two things in it. It's got an integer called P and an integer called Q. It's the same in the linked list and in the array. Let's consider an operation where we're just going to go through all the elements in our array or all the elements in our linked list and sum the value of P. So we're just going to add up all the values. So we're going to add up what's in array element 0's P, in array element 1's P, and so on. So we're going to effectively do, so I'm just going to add them all up. We'll do the same with the linked list as well. So we're going to set what the first thing is to point to P, and that one then I'm going to go to the next one and add up its value of P, the next one, and so on, and we'll add them all up. Why are we using this sort of thing? Well, the unique thing about this is that it's going to visit every single element in either the array or every single element in the linked list. So we're going to visit every single element. If you only have to visit one element, then the very nature of random access into array means it'll be faster. There's no way you can make any difference unless it's the first element. If you only want to ever access the first element, then it'll be the same speed. But if you want to access a random element, then the array will win hands down. You can just think about how it works. That'll be the case. We're going to consider we want to access every single element and do something to it. And in this case, we're just going to sum up the values. But it could be, if these were representing, say, windows on the screen, we want to move them around, we want to redraw them, whatever it is, we're going to do something to every single one. So we sort of set out the problem. We're going to go over an array of values and a linked list of values, and we're going to do something that visits all of them. We're just going to add up all the numbers stored in the element P, which is part of the structure. So what I've done is I've written two C programs which are more or less identical. I'm going to create 125,000 elements in my array, or in my linked list. And in the linked list, I've got a structure which contains an integer P and an integer Q. And in the array version, I've got a structure which contains an integer P and integer Q in the array item. The only difference is that the linked list has one extra item, which is the next pointer to the next thing. So I've written this in C, so hopefully we'll go as fast as we possibly can. Most of the rest of the program is identical. So I have my main routine here, which creates a list or an array of random numbers. So we generate 125,000 random numbers, which is the slowest part of the program, as you'll see, and then stores them. So we allocate memory for each element in the linked list, and then we set the value. Everything else we just leave as 0, and we do the same with the array, just as we did it on the paper. We then run the program 100 times. And what we're going to do here is time how long it takes to run a function which adds up all the numbers either in the list or in the array. And we'll do that 100 times, and then we can work out the average time it takes to calculate one. And we'll print out the values as we go. So we're just using the built-in clock function in C, which should be accurate enough for what we want to do. So the real meat, the body of the program, is this function here, sum list or sum array. Let's start with the array one because that's possibly the simplest. We set a variable to be 0, that's going to be our sum. We have another variable I, which is going to be our index through the array, and we go from I equals 0, i.e. the first element, until we get to the end, the number of elements in there. And we just say that sum equals the value that was already in sum, plus the value in the ith element in the array, A's P element. So remember, we said the array had a P and a Q in it. We want the value stored in the P space within the structure in our array. So we're just going to get them together. The list version, very, very similar. We set the sum to be 0. We say while P does not equal null, so while we haven't reached the end of the list, and we set P initially to be the first thing in the linked list, so we're pointing at that first thing, sum equals sum plus P inside P. We're using P inside P. Confusing variable names, but then I'm a C programmer. And then we set P, i.e. our pointer, to point to the next thing. So we follow the link to the next thing in the linked list. And we keep doing that until we come to the end. There are two programs about as simple as you get in terms of implementing a linked list or an array. So what we're going to do is run them, and we should get some values out of it. But we're not going to run them on the iMac. We're not going to run them on the Raspberry Pi. We're actually going to run them on the Atari behind me, which means I need a very high-tech piece of equipment. So I need a floppy disk to transfer the programs from the iMac. We're going to copy them off the iMac, and then we can run them on the Atari. So we come over to the Atari, and Sean's got his cameras in spot, we can see it. So what I'm going to do first is I'm going to run the list versions. We're going to generate 125,000 linked list values, so we'll let it run. Wait while it loads off the floppy disk. This is what it used to be like back in the 80s and 90s. You had to wait while your program ran. A while. A long while. And this is just a simple program. So there we go. So it's now initializing the linked list. It's allocating all the memory for the different elements and then putting a random number in the P value of each one. So we'll let that run. In the words of the old Hobbit computer game, time passes.
Or in the words of every Apple advert, sequence shortened. How long does this take?
A while.
What's a while?
I don't know. I've never timed this bit. It's 125,000 times however long it takes to allocate a random number and allocate some memory. Yeah.
On a clock speed of what?
So this is actually an 8 megahertz CPU. So it takes a while. The computer loaded off all the code for the program off the floppy disk into memory, and it's now running it to generate the data set that we need that we're then going to sum all the values. So everything that's happening now will happen off memory. It's just taking a while to process it.
But we are recording it in 4K, which is a slight overkill.
I hope this is all getting edited out.
No, there's extra bits.
So the program's going through now, and we'll let it run for 100 times and we'll get an average, but actually looking at the values that are coming up, I think we can safely assume that the average is going to end up being 166 clock ticks. Now when I say clock ticks, each of the machines we're going to look at are going to have different clock that they use to time things, so we can't compare the values directly, we could convert them into seconds, but we can certainly see the relative patterns between it. We'll call that 166 clock ticks. So to run the linked list version of the program, it takes 166 clock ticks. So let's now run the array version of the program. So now we're going to do exactly the same thing. We're going to allocate an array of 125,000 elements and populate them with random values. Because of the way I've written the program, it'll actually be the same pseudo-random number sequence, so the sum should be the same. And then we're going to fill each of them up and time how long that takes. And we'll now see whether an array actually is faster than the linked list or whether a linked list will beat the array.
So that, to me, looks like that little spinny thing is going faster.
Yeah, well, and I haven't just upgraded the processor while we're off camera. What's actually happening is when we allocate the space for the linked list, we have to allocate space for each element and then fill it in, then we allocate space for the next element. We could do that in a different way and speed things up, but we did that for the classic way. With the array, we allocate the whole lot in one go. So we allocate one huge block of memory. 125,000 times 8 is about 1 meg's worth of memory. So we allocate all that in one go, and then we're just going through it, filling in all the values, setting all the values. So that should be quicker, and it seems as the spinning wheel is going slightly faster.
Why would that spinny wheel go faster? Can you explain how you've coded this? If you coded the spinny wheel?
Yeah, so to give some nice sort of visual feedback while this is running, rather than just a plain white screen, what I'm doing is I'm printing every 100 elements it does. I update that thing and just printing either a dash, a vertical line, or one of the 2 slashes to make it look like it's spinning round, and over printing it, it creates a little effect so we can see that something's happened and the computer hasn't crashed. So this should be faster and we should get a value. The program's now working, and the immediate thing we see is that the array is taking about 179 or 178 ticks. So it's the same clock tick, so we can compare these two values. The array is slower than a linked list.
Hang on. Okay, all right, no, sorry, you can't argue with the... Okay.
So the numbers have come in, the computer's run 170, I'm going to call this about 178.5. We'll wait for the final average to come in, but so they're roughly comparable. Basically, there's not much in it, sort of thing, but there's probably about 200 clock ticks per second on this machine. It's probably noticeable. It's about 10% slower.
Okay, so that's it then. We can stop here, can we? That's it. We know what's what. Arrays are slow, use linked lists.
Yep, so arrays are slower than linked lists.
Got it, game over. End of video?
Yeah, end of video. You can now bring up the /computerphile. But actually, there are 2 ways you can walk over an array. We went up the array from the smaller numbers to the larger numbers, but we could also start at the larger indexes and move back to the smaller indexes. And I thought, well, let's try it both ways. Let's not have anyone posting some comments saying, no, but if you went the other way, so let's run it the other way. So I wrote a version which walks down, and because we're adding the numbers together, we'll get exactly the same answer. A plus B equals B plus A and all that. You can watch Numberphile to find out more on that, I'm sure. You'd think this would take exactly the same amount of time. So we'll just update our table to do this, and we're going to have the reverse array here, We'll just wait while it does that. So we're going backwards through the array. You might be thinking, can we do the same thing with the linked list? Well, the way we've designed the linked list, we have a pointer to the next thing in each thing, but we don't have a pointer back to the previous thing. It's a singly linked list, so we can only move forwards along it. We could design it to be a doubly linked list and have a backwards and forwards pointer, but if you think about it, if we started at the end and moved backwards, that's going to be exactly the same operations as if we start at the beginning and move forward. So there's actually no point in testing it. It'd be exactly the same code. We'd just be using different offsets into memory, so it'd take exactly the same amount of time. While we wait for that to do its thing, let's run the same programs on the iMac and see how much faster it is. So let's compile them up. I am turning on, as I did before, all the optimizations for the array and things, so it'll make it go as fast as possible. So I'm going to compile this up to be array test, and I'm going to compile up the speed test. Done, and I'm going to do the same thing for the link test.
I'm going to say something really obvious now, but it's obviously a heck of a lot quicker on this machine just to get compiled up and ready, isn't it?
Yeah, so this machine is much faster, which is why I'm compiling everything on here and then transferring it across, rather than trying to get my old C compiler going on the Atari. And also, the chances are this will produce better code, so it'll make the most benefit of the speed. We compiled them up, so let's run the linked list test as we did before. Boom. It's done everything. Now you notice that took a lot quicker. The numbers are still roughly in the same order, still about 100 and around 200. But remember, this is a different clock. We cannot compare the ticks from that one to this one. They're different numbers, but we get the average here, 209.54 iMac ticks. This is 166 Atari ticks. They're much slower ticks than the iMac ticks. We can't compare that to that, but we can compare horizontally. Let's do the same now with the array test. And wow, when we did the linked list test on the Atari, it was faster than the array test. Roughly, only about 10% faster. Nothing really in it, you could say. Look at the difference on the iMac. The iMac takes 43.44 clock ticks to do the array, 209. That's 5 times faster for the array. Whereas on the Atari, the linked list was faster. So a reverse array is now going on the Atari. 114.
And that's quicker.
That's quicker than the original array, and that's quicker than the linked list. So if you do everything backwards, doogie rev, it's very good. If you do everything forwards, it's much slower.
I'm a bit confused. Is there any possibility that it's just a problem in the code or something, or are you going to reveal something to us here?
We need to delve a bit deeper here to see what's really going on. Remember, we wrote these programs in C. So we wrote these in a high-level language, and then they got compiled down to the instructions that the machine can execute. And what's actually happening here is that the instructions that the machine can execute favour walking backwards down something compared with going further upwards. Now, let's run that same array backwards program on the iMac for completeness. So let me compile that one up. And again, I'm optimizing everything to the hilt. Test, and so we'll run speed test back. And we'll run this one. So before, the array is now much faster. According to this, a reverse array should be faster than the forward array. So what would you expect the value to be, Sean, for running the reverse array?
Maybe about 15 or 20 then.
So you reckon?
If it runs the same as that did, then.
Right. Would you like to stick with that answer, or would you like to change that?
No, I've decided, actually, because the Atari was faster to do a linked list than an array, and the iMac was the other way around, I'm going to say it's going to be slower to do it in reverse.
So you reckon it's going to be slower to do it in reverse? Oh, I do like an indecisive person. There we go. Average time, 47.46.
So marginally slower.
Marginally slower. About 10% slower. But still an order of magnitude faster than this. We could do the same on the Raspberry Pi. So again, we'll compile all of these up. So we'll do array test, compile that up, noticeably slower to compile. We'll do the LL test. This is the list version. And we'll do the reverse test. So compile them all up on the Raspberry Pi. So let's run these and get the numbers. We'll run the array test. We now get 965.75 as our average for the array. We'll run the linked list and we get 1858.61 for the linked list test. And now we'll run the reverse test and we get 1019.55. So we've run the test now, so we've assumed nothing, we've ran some tests to actually get some data so we can see which is faster, an array or a linked list with this operation we've been trying. And we've got some pretty interesting results. So when we ran it on the Atari, the linked list was faster than the array, unless you ran the array backwards, in which case the array was faster than the linked list, and the array going forwards. We'll come back to that. We ran it on the Raspberry Pi, and here the array was about twice as fast as the linked list, but if you ran it backwards, the array was slower. And if you did it on the iMac, the array was 5 times faster than the linked list, whichever way you went. So what's going on here? Well, let's ignore the iMac for the minute. The Apple haters will love that bit, but let's ignore the iMac for the moment. Let's just have a look at the Raspberry Pi and the Atari. So we've got the Atari and the Raspberry Pi, and we'll just go with the array speed and the linked list. So they've got about 179 for that and 166 clock ticks for that. Now remember, we can't compare the clock ticks between the different machines because they're different clocks used in the machines, but we can compare them relatively between the same thing on the same machine. For the Raspberry Pi, it was 966, and that was a 1,859-ish. Now what's going on here? Well, the thing we need to remember is if you look at the machine code, it's roughly the same length, it's the same number of operations. Now on the Atari, some of the instructions will take slightly longer than others to execute, but that's not what's going on here. We need to think back to the video on caches that we did. The difference between the Raspberry Pi CPU, other than it being much faster and more modern, and the Ataris, is that the Ataris doesn't have a cache. So every instruction it needs to fetch, every bit of data that it needs to fetch, has to be fetched from memory each time. It's not cached. Broadly speaking, there is something going on there, but broadly speaking, there's no cache. There's about is a prefetch buffer if you want to get into the details, but we can assume there's no cache. So if we think about the CPU in the Atari, then it's having to access memory for everything. So everything that the CPU needs to fetch on the Atari, the instructions, the data from the array or the linked list, and of course the next pointer from the linked list, has to come from memory. So it takes the same amount of time regardless of whether it's fetching data or fetching instructions. On the Raspberry Pi, however, we've still got the main body of the CPU, which is going to execute things, and it has memory as well. But in between there, we have a cache. In fact, we actually probably have 2 caches, one for data and one for instructions. And so when the CPU accesses it, as we looked at in the previous video, it accesses it via the caches, and then they, if they haven't got it, get it from memory. So why does this make a difference? Surely things will still work out the same. Well, on the Atari, the fastest thing in there is basically the memory. The memory is much faster than the CPU. It's about twice as fast. And so the memory can provide the data exactly when the CPU needs it. So there's no real need for a cache. Move ahead to the Raspberry Pi and the iMac, of course, then the CPU is much faster than the memory. So when the CPU asks for something, it has to wait while the memory provides it. Now let's think about what happens when we run our program with the array on the Raspberry Pi. Every instruction, after the first time it will be accessed, will be cached in the instruction cache. So the first time we go through the loop, all the instructions that are going to be used in that loop will have been cached in the instruction cache. So you can get these immediately. The data, particularly with the array, but also perhaps a bit with the linked list, we don't get just 1 or 2 bytes each time. We'll get what we call a cache line, so perhaps 128 bytes in a go. So we'll get some of the data that we already need into the cache as well. So some of the data will already be there in the array, more so with the array. So the reason that the array runs faster on the Raspberry Pi is that all the instructions are coming straight out of the instruction cache. It basically gives us a fast lane for those instructions, so they get there immediately. So it's only the data that it needs to get from main memory, which will get cached as well. So the same happens with the linked list program, except for one crucial difference. With the linked list program, we have to make one memory access to get the data value that we're going to sum. And then we have to make another memory access, which has to go through the cache into main memory for the address of the next thing. So we have to make 2 memory requests, which may get satisfied by main memory here. Whereas with the array one, we only have to make one for the value that we're interested in. And because of the cache, we get sort of a fast path for the instructions. And so actually not having to do that second memory access to get the next pointer here means that the array version of the program ends up working about twice as fast. On the Atari, because everything is coming from memory, it doesn't matter whether you're reading an instruction or reading a bit of data, it's still got to come from memory each time. So actually, the fact that the value is already pre-calculated in memory means that that actually runs slightly faster. I mean, we're talking perhaps 10% faster, not really anything. So we get a slight speed benefit. Now, to show that this is the case, I took the same version of the program on the Atari and ran it on the Atari Falcon. Now, the difference between the Atari ST we use there and the Falcon is that the Falcon has a slightly later version of the 68000 processor, which has a cache in it, both instructions and data cache. And when I ran that on there, the times it came out, so the array was 46 clock ticks, it's a much faster processor anyway, and the linked list was 58.5 clock ticks. So on the Falcon, because you've got the cache there, just like on the Raspberry Pi, the array version ends up being faster. Exactly the same program, exactly the same machine code. Because you've got the cache there, the array version ends up being faster because the instructions are there to be fetched on that sort of fast path from the cache rather than having to go to main memory each time, mean that the array version becomes faster than the linked list version. Now, a couple of other things we haven't talked about yet. Why is the reverse array faster on the Atari? Simple answer to that. It just uses slightly different instructions. There are instructions on the 68000 that allow you to do a decrement, test if it's 0 and branch if it isn't, all in one instruction. So you can actually make the code slightly more compact and run slightly faster. Again, it's a small enough time. Why then is the iMac significantly faster? We're getting sort of 5 times faster. Well, that's because I used a slightly different compiler there. I used the Clang C compiler on the iMac rather than GCC for the other two. And it cheats. It spots that you've got an array accesses in a loop, and it says, well, okay, rather than doing a loop around 1 array access, I will do a loop around 8 array accesses all in one go. So it actually removes some of the tests for the loop, and it makes the program much faster. So the compiler is being clever and optimizing the program so that it runs faster. The answer to whether an array is faster than the linked list or not very much depends on how your CPU and the machine that you've built is configured to actually execute the code. So you can't make assumptions about how a CPU will execute code. You really need to do the tests to see what's happening. Even within the same architecture family, the difference between the 68000 and the 68030 in the Falcon mean that assumptions we make based on what the Atari ST did, where the array was slower than the linked list, aren't true on the Falcon. And when you move it onto a completely different architecture like the Raspberry Pi or the x86 chip in the iMac, then again you get different effects. So the best thing is when you're faced with a question like this and you're not sure, come up with some tests and collect real data and you'll be able to see what's going on.